to look at work. So we're jumping ahead to section 6.4, I believe, which is on, what page was that? 500-ish, 556, 7? I don't know. 557. All right. And we will work some stuff out. So, hey, life's a word problem, work it out. All right, what is work? So let's define what work is, okay? Work basically is going to be defined this way. If a constant force, so we're gonna look at a force. A force would be like pushing something. So like when you're lifting weights, you're pushing against you're bench pressing, you're pushing up against the bar and the weights, right? Now, if you do that consistently, that would be a constant force, right? But one thing that we know is a constant force pulling against you is gravity, right? So that'd be against you, and you got to outweigh the gravity and push the other way. So, but anyway, so let's just look at this. If a constant force, so we're going to look at a constant force against something, and we're also going to look at a variable force, like where the force changes, okay? If a constant force is applied to move an object, so we're trying to move objects. So we're trying to move an object by applying a constant force applied to move an object a certain distance. Okay. Then the work done, I hate writing stuff out. I should have had this already written out. Then the work done, like I do on my board videos, then the work done on the object by the force. So on the object by the force is given by, I'm just going to cut to the chase. It's given by the product of the force times the distance. So the work W, we're going to call the work W, is the force, which we're going to, I am your father. Oh, no, not that force. But anyway, force times distance. Okay, so I'm going to call little d the distance. Capital F is force, because little f, of course, typically is a function, so we don't want to confuse that. So we're using capital F. Now, if this, let's say the force is in pounds, and the distance is in feet, then the work would end up being in foot-pounds, is how we say that, would be the label of work. So a common English measurement, God save the Queen, Bucky, would be foot-pounds. So let's just look at an example of this. Example, if I have a force of 25 pounds and I want to move an object 10 feet. And it'd be a constant force. Constant force of 25 pounds is applied to an object to move an object 10 feet. What work is done? Then the work, once again, is force times distance. So in this case, the force is 25 pounds times 10 feet is 250. Of course, what's the label? Foot-pounds. So pretty simple deal on, when we have a constant force to figure out what the work is based on the distance, right? So the challenge is, and why we need calculus, what does calculus measure? I defined it day one, instantaneous rate of change. So if we have a non-constant force, IROC, right? So if we have a non-constant force, what goes on with that? Non-constant force. But anyway, so we got a non-constant force, and let's say, of course, you know, we can't, I mean, you could push something backwards, right? Like if you have a start point, we could have negatives there. So, I mean, it is appropriate to draw left of 0. But anyway, if we're trying to move something from A to B, if it has a variable force, and of course there's any point in there, you know, any point X in there, we'll just call it X. So if an object moves from point A to point B subject at each point X to a variable force, so we're going to say X is subject to a variable force or a varying force. Okay, we're gonna call that. We could call it f of x. We're gonna use little f of x. It is a function, and it's gonna change based on what x is. So maybe if I push harder as I get closer to b, the force would be an increasing force, right? If I push less hard or I get tired, you know, as I go, then the force would be decreasing. But if we let's let this be continuous, is continuous. Let's let it be a continuous function. That's going to make life easier. Continuous where? On A to B. I don't really care outside of there what's going on. But anyway, what I could do is I could partition this up, and I could look at a little subinterval, and I'm just going to call it x sub I minus 1 to x sub I. And let's just look at that. And so for this little piece of the interval, while I'm pushing on there, of course, that's delta x, right? And instead of delta x, it's the ith interval. So we're calling it delta sub ix, if you remember kind of breaking down on summations and antiderivative, like integrals, right? So that's delta sub ix, right? And so we have, you know, if I wanted 10 of these intervals, I divide by 10, right? And they'd all be the same size. But the reality is I could let the number n, if n is the number of intervals, I could have n be 100 or a million or a billion or whatever. I could let n go to infinity. They would all be the same size, right? But really, you know, maybe I want some intervals to be smaller than others, and that's the norm of the partition. And so what we're going to do here is we're going to add up the work. So the work, the change in the work for the ith interval is going to equal, well, this is going to be the work done on the ith interval. Okay, so that's work done on the ith interval. All right, and then what we can do then is we can add them all up, can't we, to get the total work? So what I'm going to do is the total work then, which I'm going to go back to blue because we're going, you know, the full, trying to figure out the work on the full interval. So the work done on the full interval is going to be the sum, I equals 1 to n, if I have n in intervals, of the delta sub w sub I, the change in the work for each one. Okay, so we're going to, the tiny amounts of work done in each subinterval, we're going to add them all up. That gives us the total work, right? Now, if we want to be exact or precise, what are we going to do? We're going to let those intervals get smaller and smaller and smaller, correct? So the reality is we come up with a very nice thing here that I can say, hey, the work done is going to be the limit as the norm of the partition. The norm of the partition goes to 0, correct? Or basically, if we were having them all be the same size, you know, we could say the limit as n goes to infinity, right? Adding up n exact ones, but I'm not going to do that here. So I'm going to take the norm of the partition. Now that really we could put delta sub I there, the norm of the delta, the size of the ith partition, the largest subinterval. Remember, norm is the largest subinterval. But anyways, the norm of the partition goes to 0 of the sum of f of, now we're going to need some point in there. But anyway, the sum of the work. So what did I have written down? Sum of the delta sub, change the works, right? I equals 1 to 1 to n there. Okay, so we have that, and then of course what's this? There's going to be some point in there, so I'm gonna draw it out. There's A to B again, right? And I'm going to go back and I'm going to draw that subinterval, x sub I minus 1 to x sub I, and just that little distance there. You know, this is delta sub I x is the distance, right? So what's work? Work is force times distance. So it's going to be the force in there times the distance. So the distance is delta sub I x, correct? And what's the force? Well, the force is there's going to be some point in there. Since it's a continuous function, we know that there's some point in there that I could just say, hey, and I'm going to call it, let's just call it t, or t sub I. So let t sub I be the one where the force evaluated at t sub I is going to be the same as the average force on the entire interval. But anyway, I can do this, but it's force for that interval evaluated at a particular point times the distance, right? We add them all up. Long story short, because we have a continuous function, is the main thing here. This ends up leading us to the work formula. The work formula is going to be, this ends up being a Riemann sum, so a definite integral on a continuous force function. So we're going to take the definite integral to add up those infinitely many, as we approach infinity or the norm of the partition approaches 0. To add all those up, we can take the definite integral from A to B of the force function f of x with respect to x. So ultimately, once again, I'll let you read through the book's version of how they develop this. This is really what you need to know. Just like we needed to know the arc length, right, yesterday, we can come up with a formula for a work function for a varying force. Okay, now let's talk about Hooke's law. Hooke, Dr. Hooke. Wait, Dr. Hooke. Your parents might know Dr. Hooke. He's got some good songs. Some are inappropriate for juniors in high school, but anyway, the force required. So Hooke's law, the forces. So this is physics applications, right? So somebody going into physics and engineering. The force required to displace the end of a spring. So think of a spring. So if we have a metal spring, right, and then you can stretch it, right? But some springs are harder to stretch than others, right? It takes more force. So the forced. Who wrote the forced? Isaac came up and put a D on there. The force to displace. The force to displace the end of a spring. Okay, so think if you go home and look at your garage. I mean, some garages, have chains, some have springs that help kind of pull that door up and they stretch out, right? So the spring gives some work to help lift. But anyway, this is proportional to the displacement. The displacement is how much it stretches, right? How far? So it's a distance. So that's Hooke's law. So if I've got a spring here, and then I end up stretching it out, is direct proportionality. Remember that? So it's just some constant times x. So K is the spring constant. This is the spring constant. Okay. So the spring is always pulling course until it gets stretched out, right? But anyway, a spring typically holds it better for a while anyway. So that's the spring constant. So this is just direct proportionality. So that's Hooke's law. So what we're going to do is we're going to do an example of this. This is going to be an example much like number 8 in your book. But anyway, so let's just look at this. A spring has natural length of 8 inches. All right. So if a spring has natural length of 8 inches and it takes 4 pounds to stretch it 2 inches. So let's assume that it takes 4 pounds. Now what's that? 4 pounds. What is that? I mean, you could think it's force, right? That's the force. It takes 4 pounds to stretch it. So think about this. I mean, you know, if you're ignoring gravity pull, but if you put a weight at the end of a spring and it stretches it down, right? Okay. Of course, you got the gravity pull as well. But anyway, if we're lateral and we're taking that out of it and we're just pushing, stretching it, so we're going to go left to right. We're going to stretch it from left to right, not up and down. So so gravity is not coming into play here. But it takes 4 pounds to that's not right, to stretch it 2 inches. Okay, 4 pounds. Find the work if we want to stretch it from 8 inches to 12 inches. We want to find the work done in stretching from 8 inches to 12 inches. Okay, well, here's the deal. Is it going to be more or less work than 4 pounds? More or less force. It takes 4 pounds to stretch it 2 inches, but we're trying to stretch it 4. It's going to be more. Do you think it's going to be double? Do you think it's going to be 8? So you think the answer is 8? Okay, well, I don't think so. But anyway, but let's find out. So that would make sense. You know, if it was a constant, it doesn't say every 2 inches. What happens is, as that spring, think of a spring, as you stretch it farther, it gets harder. And if you're not familiar with that, like, you know, you get the rubber bands, right? We talked about that. Like you're doing the running and they're pulling against you, right? The farther you go, it's harder, right? So that kind of happens. That definitely happens with a spring as well. So anyway, that's okay. It's nice to have you get baited in. I wish fishing was that easy. So let a couple things here. Let f of x equal the force needed to stretch it x feet. Now I switched. I didn't say inches here. We're trying to stretch the spring x feet. Now, could you use inches? Maybe. I'll let you go back and try and work this all in terms of inches. Okay. But anyway, I'm not going to do that because I already got it worked out. And anyway, then what do we know? Then f of x equals kx, right? Where k is the spring constant. And we need to figure out what that spring, do we know the spring constant? Was that given? It wasn't given, was it? So we need to figure it out. How can we figure it out? But it's constant, right? So that's Hooke's law. So we are utilizing Hooke's law here. But we know that f of any value x is k times that x, right? And so if I want to know, we know we were given something here, 4 pounds of force to make it go 2 inches. Well, 2 inches as a foot, make that feet, 1/6. So F evaluated at 1/6 of a foot is going to be K times X, which is 1/6, right? And of course, what's it equal? What is F of 1/6? 4 pounds. Okay. So the force is 4 pounds for that 2 inches. So that's K times 1/6. right? By the way, so, and why did I do feet and not inches? Because normally work is in foot-pounds as an English measurement. Doesn't mean it has to always be foot-pounds. I mean, inch-pounds, yeah, you could do that. It's just awkward, right? It's kind of like using centimeters instead of inches, right? Awkward, even though it makes complete sense because it's a base 10, so whatever, right? Anyway, so K equals what? K is 24, right? We just multiply. So K is 24. I can plug that in right there. And then that's going to imply that f of x, my force function, is now 24x. Okay, where x is the number of feet, right? So let's so I'm gonna draw this like I need a bigger board. But anyway. And Isaac's, well, I couldn't be more bored. Anyway, but we had 24x. So here's my spring, right? So I've got that, and I'm taking it, that's where it is normally. Normally it's 8 inches, right? So this is 8 inches here. And basically, 8 inches is what? 2/3 of a foot? 2/3 of a foot. By the way, 2 tick marks is inches, 1 tick mark is feet, right? Anyway, and then what I'm going to do, I'm going to use a different color here since I did before, but I'm going to take that out and I'm going to pull on it. I'm using force to pull it out, but I'm trying to get another 1/3 of a foot, right? So really the interval I'm trying to go for here goes from 0 to 1/3 as far as feet go. So this is x feet to the right, right? I said we're going to stretch it left to right. Remember that? All good? So hopefully you understand the concept, what we're trying to do here. Of course, now what can I do? What is the work defined to be? So remember, 1/3 of a foot, that's 4 inches. I was trying to stretch it 4 inches, not 2, right? That's why I went from 0 to 1/3. So the work done is going to be the definite integral from 0 to 1/3 of the force function, right? So a to b of f of x dx, which f of x is 24x, right? So this is the definite integral from 0 to 1/3 of 24x dx. And you see how beautiful calculus is? So, I mean, honestly, this is part of why I wanted to go over this stuff, because there are some applications that if you use calculus make life so easy. Anyway, so we got 24x squared, 24x squared over 2, right? So that's 12x squared evaluated from 0 to 1/3. Plug in a third. Of course, if I plug in 0, it's 0. So it's 12 times 1/9 is 12/9 or 4/3. And what's the label? Right. So the work equals 4/3 foot-pounds. Okay. Torque. I mean, it's rotational. So I mean, yeah, I mean, there's going to be some similarities there, but it's your force is rotational, not linear. So, but that's a great question.